Hello everyone and welcome to ETEC221 lectures series. Today's lecture is first one, lecture 1, Fundamentals of Analog to Digital Conversion. Electronics is a relatively recent technology that has undergone explosive growth. It is now widely spread, that is, touches all of our lives in many ways. The field of study we call electronics encompasses a broad range of specialty areas, including audio systems, video systems, digital computers, communication systems, instrumentation and measurement, automatic and control systems, robotics, and so on. Each of these areas in turn has its own specialty areas. However, all electronic specialties are the same in one aspect. They utilize electronic devices like transistors, diodes, integrated circuits, optoelectronics, and various special components. The electrical characteristics of these devices make it possible to construct circuits that perform useful functions in many different applications. Electronics, as you may know by now, can be divided in two major groups: digital electronics, which recognize or produce only several limited number of states, 2 states to be precise in case of binary electronics. The second group is analog electronics, which responds to or produce an infinite number of states within defined limits. Since most of things we observe or measure is of analog nature, for a long time all electronic circuits operated in the analog fashion. If you want to amplify your voice, you will use analog amplifier. However, telephone switching and computer technology forced engineers to explore digital electronics, electronic devices which operate very often, very fast, and with a high reliability in the same way over and over again. Analog electronics is not suitable for this task. For decades, those two groups have been developed independently and separately, not having much in common. However, the demand for connecting them somehow has become more and more prominent, especially in modern electronics, so that the special group of electronic devices had to be developed with the sole purpose of interfacing two worlds. In analog presentation, one quantity is represented by another one which is proportional to the first. For example, in an automobile speedometer, the angular position of the needle represents the value of auto speed, and the needle follows the variation that occurs as the car speeds up or slows down. Another example of analog quantity representation is an audio microphone in which an output voltage is generated in proportion to the amplitude of the sound waves impinging the microphone. The output voltage follows the variation that occurs in the input sound. Analog quantities such as those cited above have an important characteristic that they can vary over a continuous range of values. The car speed can have any value between 0 and say 150 km per hour. Similarly, the microphone output might be anywhere within the range of, let's say, 0 to 10 millivolts. In digital representation, the quantities are represented not by proportional quantities, but by symbols called the digits. For example, consider a digital watch, which indicates the time of the day in the form of decimal digits representing hours and minutes, sometimes seconds as well. The digital watch reading does not change continuously. Rather, it changes in steps of 1 per minute or per second, while the time of the day changes continuously. In other words, this digital representation of the time of the day changes in discrete steps in comparison to the representation of the time provided by an analog watch, in which the dial reading changes continuously. So the major difference between analog and digital quantities can be simply stated as follows. Analog means continuous, digital means discrete or in steps. Now let us try now to define analog and digital systems. An analog system contains devices that manipulate the physical quantities represented in analog form. In an analog system, the quantities can vary continuously over a range of values. For example, the amplitude of the output signal to the speaker in radio receiver can have any value between 0 and its maximum limit. Other common analog systems are the magnetic tape recording and playback equipment, automobile odometer, and the telephone system. A digital system is a combination of the devices designed for manipulating physical quantities or information presented in digital form. In other words, they can take only discrete values. Such devices are mostly electronics, but they can also be mechanical, magnetic, or pneumatic. Some of the familiar digital systems are calculators, digital watches, digital computers, traffic signal controllers, and so on. What are merits and limitations of digital techniques? Digital systems are easier to design, as the circuits employed are switching circuits where values of voltage or current are not important. Only the range, that means either high or low, in which they fall is important. Storage of information is easier, as it is accomplished by special switching circuits that can latch into information and hold it for as long as required. Greater accuracy and precision, as digital systems can handle as many digits of precision as needed simply by adding more switching circuits. In analog systems, precision is usually limited to 3 or 4 digits because the values of voltage and current directly depend on the values of circuit components. Programmable operation, as the digital systems can be easily designed for operation controllable by a set of stored instructions called a program. Analog systems can also be programmed, but the variety and complexity of the available operations is severely limited. Digital circuits are less affected by noise, as spurious fluctuations in voltage, that mean noise, are not as critical in digital systems because the exact value of the voltage is not important, as long as the noise is not large enough to prevent distinguishing a high from low. However, there are limitations. There is really only one major drawback of using digital technique, and that is due to the fact that the real world is mainly analog. Most physical quantities are analog in nature, and these quantities are often the inputs and outputs that are monitored, operated on, and controlled by a system. The need for conversion between analog and digital forms of information can be considered a drawback because of additional complexity and expense. Another factor that is often important is the extra time required for performing these conversions. In many applications, these factors are outweighed by the numerous advantages of digital techniques, and so the conversion between analog and digital quantities has become quite common in the current technology. So how the practical bridging between two worlds of electronics should look like? An analog voltage represents a continuous process that may vary continuously over some voltage range. It might have an infinite number of values between its minimum and maximum voltage limits. Most of the physical variables are analog in nature: velocity, weight, pressure, temperature, distance, height, and so on, can have infinite number of values. In contrast, a digital signal can have only predefined number of levels. In binary systems, we said, there are only two different and useful levels, a low level and a high, such as 0 volts and 5 volts. These voltage levels are used to represent numbers in binary numbers system, which has only two digits, 0 and 1. Digital computers perform computations using binary numbers represented by digital voltages. Interfacing these two worlds requires special electronic circuits which will understand analog values and then transform them to some form of digital signal recognized by computers and other digital systems. Converting an analog value to a digital equivalent binary number is called digitizing the value. After a digital system has transmitted or processed digital data, it is often necessary to convert the result back to analog domain. This function is performed by a digital to analog converter, or DAC, or DA converter. A digital to analog converter having 4-bit binary input produces only 2 to the power 4 16 different analog output voltages. One could say that this is not truly analog output variable because it cannot have an infinite number of values between its minimum values and maximum. An 8-bit binary input can produce 2 to the power 8 256 different output values, which is still not a true analog value, but it is a much better presentation of an analog variable for the same range of analog values. This means that the greater the number of input bits, the greater the number of output values, and closer the output resembles the true analog quantity. Resolution is a measure of this property. The greater the resolution of DAC, the finer the increments between output voltage levels. Let's discuss some functional requirements for digital to analog and analog to digital conversion. Because most sensors have an analog output, while much data processing is accomplished with digital computers, analog to digital and digital to analog conversion obviously play an important role. The process of changing an analog signal to an equivalent digital signal is accomplished with the help of an analog to digital converter, or ADC. For example, an ADC, or an analog digital converter, is used to convert an analog signal from a transducer measuring some physical quantity such as temperature, pressure, position, rotational speed, or flow rate into an equivalent digital signal. An analog to digital converter is often referred to as an encoding device, as it employs for encoding signals for entry into a digital system. So on the left-hand side, you will see block diagram of analog to digital converter. As you can see, we have input analog signal and the output will be digital code. So that's why we said that analog to digital conversion is the process of taking one analog value of the voltage or current and converting it into a proportional digital code, such as a simple binary or BCD code. Analog to digital conversion is accomplished by the use of analog to digital converter, abbreviated as A/D converter or ADC. On the right-hand side, we have a block diagram simple block diagram of digital to analog converter. Of course, here the input will be digital code, here assumed to be N resolution digital code, and the output, of course, will be analog voltage. Digital to analog conversion is the process of taking a value represented in digital code, such as simple binary or BCD code, and converting it into a voltage or current which is proportional to the digital value. D/A conversion is accomplished by use of digital to analog converter, abbreviated as D/A converter or DAC. To summarize this introduction so far, we can say that analog signals can vary continuously throughout the defined range, and that the digital signals take on specific values only described by a binary number. Most of the signals, as we said, directly encountered in science and engineering are continuous. Light intensity that changes with distance, for instance, voltage that varies with time, a chemical reaction rate that depends on temperature, and so on. Analog to digital conversion and digital to analog conversions are the processes that allow digital computers to interact with these everyday signals. Digital information is different from its continuous counterpart in two important respects. It is sampled and it is quantized. Both of these restrict how much information a digital signal can contain. This chapter is about information management. That means understanding what information you need to retain and what information you can afford to lose. In turn, this dictates the selection of the sampling frequency, number of bits, and type of analog filtering needed for converting between the analog and digital realms. Now, with the introduction of new types of electronic devices, a general concept of analog to digital and digital to analog conversion should look like illustration shown. On the left-hand side, we have analog world. Many of the analog physical phenomena need some kind of a transducer that will generate corresponding analog signal, voice or voltage or current. For instance, a voice, or generally the sound, needs a transducer called microphone, where changes in acoustic pressure are converted into proportional voltage variation. Similarly, we need a camera as a video transducer to convert images into electrical signal which describes the image content. Further, all of these physical events must have appropriate transducer which produces required analog signal. These analog signals are now converted in analog digital converter into a digital format, as can be seen from the time waveform with only few distinct and discrete levels. Typically, on the other side of data transmission system, there is a load which utilizes analog signal again. Therefore, digital to analog conversion of digitally coded signal must be performed before the signal can be recognized by load. When an analog signal is created again, it will feed corresponding transducer for final utilization. For instance, in case of sound, a transducer called a speaker will convert analog signal into acoustic pressure variations. If necessary, this analog signal can be amplified or attenuated depending on a particular application. For images, we will use the transducer called TV or monitor display. Sometimes we use analog signal to produce rotational motion of a motor, like in case of servo motors, which are generally called analog actuators. However, there are situations when digital to analog conversion is not required, so that we can utilize digital format directly, like in case of numerical displays or digital instruments. In this functional block diagram, a more specific type of processing is shown when microcontrollers are involved. On the input side, you can notice a block called MUX, multiplexer. Using these electronic devices, we can provide analog-digital conversion of multiple analog signals with only one analog-to-digital converter. Instead of using one analog-digital converter for each analog signal, which is usually a very expensive solution. These multiplexers scan each of the inputs periodically, connecting them briefly to the same analog-to-digital converter via interfacing amplifiers, like differential op-amps, operational op-amps, instrumentational op-amps, or isolation amplifiers. Obviously, analog-to-digital converter performs conversion on only a short portion of each of the multiplex analog signals. When microcontroller completes the program task, digital to analog converter revert digitally coded symbols back to analog domain. Required analog processing can take place if necessary, and then the signals interfaced to the output multiplexer using any of the already mentioned amplifiers. The input and output multiplexers must be synchronized so that each input signal is correctly connected to corresponding output lines. We already mentioned that not all points of analog signal can be converted. We have to give up some of the integrity of analog signals by adjusting them to digital coding, which includes two modifications: sampling and quantization. On the left-hand screen, we have original analog signal, and on the right-hand side is the same fraction of the signal after being sampled. We say that the sampling is a process of substituting the entire analog signal by periodic samples, thus creating a train of pulses. It converts time from continuous to discrete variable. Changes in an analog signal between these discrete intervals are ignored. So let's take a closer look into a sampling process. Here is the simplified schematic of a typical sample and hold circuitry. It is consisted of two buffers or voltage followers with voltage gains of 1. Depicted mechanical switch SW1 has two positions. In the first position, it connects the output of buffer U1, which is the same as a source signal, so that the capacitor can charge rapidly to the maximum instantaneous amplitude. In the second position, it connects charged capacitor to common for quick discharge, dropping the sampled voltage to 0. That's why the signal looks kind of chopped or sliced, as you can see from those two illustrations. Upon sampling, the next process is a quantization, which is usually inherently included in operation of analog-digital converter. This process rounds up sampled amplitude to the nearest value, which can be expressed as integer number, and it is kept at that level until new sample comes. Simply, we say that quantization is a process of digitizing the analog signal. What that means is that the sample amplitudes have been substituted by integer number. So on the left-hand side, you have a sampled analog signal. On the right-hand side, you see digitized signal. Now, the difference between actual amplitude and quantized amplitude, or rounded up amplitude to the nearest integer number, is called quantization error. This difference is presented here on the third screen as quantization error, or sometimes called quantization noise, because the amplitude of this different signal looks pretty much like a random signal. By now it should be obvious that the number of quantization levels depends on resolution of the digital to analog converter. Now these snapshots show the result of digitizing the same analog signal by the converters with the different resolutions, different number of bits. The analog signal is a sawtooth signal as displayed on screen A, and we presented here the shapes of the converted signals by a 3-bit, that's B screen, 4-bit, which is C screen, and 5-bit digital to analog converter, which is shown in screen D. It is quite clear that the higher the bit number, the better the resolution is, the more closely the converted shape matches the original analog signal. In practice, we will have to compromise between the acceptable quality of the conversion and corresponding complexity, speed and cost of the converter to provide this quality. And this will conclude the Lecture 1, Fundamentals of Analog to Digital Conversion. Thank you.